have a barrier with two openings, and we got a wave, particularly electromagnetic radiation, visible light probably, coming towards that barrier through those two openings. Of course, we know that that visible light, that electromagnetic radiation, that wave of whatever type is going to diffract. It's going to spread out. In fact, it's going to diffract and spread out twice through both openings, and it's going to produce an interference pattern. The interference pattern that we observe if it's light occurs on the screen that's on the other side. And that interference pattern is going to be a pretty predictable pattern. We're going to get a bright spot in the middle. We're going to call that a maximum, specifically our central maximum. We'll assign a number of 0 to it. Beside that, you're going to get a dark spot. We're going to call that a minimum or a node. Beside that, we're going to get another bright spot. We're going to call that maximum number 1 or antinode number 1, the first order maximum. Then a dark spot, then a bright spot, then a dark spot, then a bright spot, and so on. And we get the exact same pattern forming on the other side with the exact same distances and angles and so on involved on both sides. All right. Get two equations that we know that we can use to analyze this situation that we sometimes call Young's double slit experiment. Okay, it was performed first by a guy named Thomas Young, and it was one of those experiments that verified the wave nature of light. Those two equations are lambda is equal to d sine theta over n, and lambda is equal to xd over n times L. One of these equations is valid all of the time. Okay, it's 100% correct all of the time. One of these equations is a good approximation most of the time, but not all the time. Which one is the one that should get the check mark here? Which one is the one that we can use all the time, no matter what? Yep. Good, d sine theta over n, the first one. We're allowed to use that whenever we want, as long as we have the right variables in there, right? The second equation is valid if theta is less than about 10 degrees. Now, we don't calculate theta every single time. We could calculate theta and decide whether it was under 10 degrees by looking at the number for theta. But there's an easier way to do that. There's a rule of thumb. What's our rule of thumb? Yep. Good. We're going to take the value of x, we're going to multiply it by 10, and we're going to compare it to the value of L. If L is greater than 10 times x, then we're for sure going to be under 10 degrees, and we're allowed to use that equation. All right? Let's take a look at some of the variables here. Lambda, of course, is the wavelength. Okay, done deal, easy. D, we got a few distances involved here. What's D? What's D going to be, Cole? Good, distance between the slits there. That's going to be a pretty small number, obviously. X, what's X? Another distance, right? But what distance is it? Because we got a bunch of them here. What's X going to be, Zane? Yeah, node to node, or antinode to antinode, or node to antinode, or whatever the heck we want, really. X can be whatever we want up there. Any distance from node to antinode, and antinode to node, and so on and so on. We got to be careful, though. If we're making X whatever we want, n has to be consistent with that value of X. What's n going to be in this first case up here? First antinode, fourth antinode, n's going to be equal to what? Red? 3, good. What about this one? This one's a little bit harder. What's n going to be here? Central antinode, or central bright spot, and then we've got the 1, 2, 3, fourth order node. Fourth order node as opposed to antinode. Braden, what's n going to be there? Good. And this one's the hardest one of the three, I think. We're going from the 1, 2, third order node on one side to the 1, 2, third order node on the other side. Kelsey, what's n going to be in that case? 5. Third order node on one side, third order node on the other side. Oh, sorry. No, you're right, actually. No, you're right. How's it going? No, you're absolutely right. You got me. You're smarter than I am. Okay. What was I thinking? What was I going to say? I was going to say 6. Right? Because third and third gives me 6, right? Except it's not the third and third. It's the third node and the third node, which gives you 2.5 and 2.5. So n is equal to 5. Good. How would we change the question to make what I was thinking the correct answer? Yep. Good. Yeah, that's what I was thinking. It's third order antinode to the other third order antinode on the other side. Good. Good. Thank goodness we have you here, Kelsey. Pick up the slack for me. What if we have more than two holes? What if we have more than two openings here? We have a diffraction grating. Instead of having two openings a certain distance apart and a value of D, we got this we have this piece of glass or piece of plastic, and then we have etched into that piece of glass or plastic a whole bunch of openings there. We call that a diffraction grating, right? That diffraction grating will allow light through it in the same way that the two openings allow light through it. It's going to produce a pattern on the screen that's essentially the same as what we see right there, except the value that we're going to have here that goes with that diffraction grating is not going to be D, rather it's going to be the lines, probably the lines per centimeter, maybe the lines per meter, maybe the lines per millimeter. What does that correspond to? Lines per centimeter, lines per millimeter, lines per meter. Not D, but 1 over D. So if you're given a value of 1 over D, then get the value of D. Okay, flip it over. Take the inverse of whatever you have there. If it's 1,000 lines per centimeter, then D is going to be 1,000 x to the minus 1. That's right? It's going to be 1 over 1,000, 0.001. Convert it to meters at that point, and then plug it into here just like you do the other questions. All right, we had three homework questions on this topic yesterday. Let's take a peek at those 3 questions now. Any issues on 693, please? Good. All right, if we had no problems with that, let's review what we did as a new topic yesterday, and that was this idea of photon theory. A photon, remember, we talk about as being a quantum of energy. It's a particle of light, a bundle of energy or a bundle of light. Up until yesterday, we talked about light being an electromagnetic wave. It still is an electromagnetic wave that has a wave nature. It still does have a wave nature, but now we acknowledge that it also has a particle nature. It has both, a wave-particle duality associated with it. It exhibits polarization. It exhibits refraction, diffraction, interference, all wave properties, but it also exhibits particle properties. And we describe the particle nature of the light using photon theory, photon being a quantum of energy or a particle of light. The energy of a photon is equal to h times f, or the energy of a photon could also be equal to hc over lambda. What's h? You don't have to tell me the value of it because we can look it up. It's a constant. Yeah, we call it Planck's constant. In fact, it has 2 values, 6.63 times 10 to the minus 34 joule seconds, and we got 4.14 times 10 to the negative 15 electron volt seconds. Which one do we use? They're both on our data sheet, so which one do we use? Yep. Usually it's whatever you want your answer to be in, yeah. Okay, whatever's convenient for you. If electron volts is more convenient, then use electron volts. If joules is more convenient, then use the 6.63 value. We had a couple questions that you were working on yesterday in class, and we're assigned for homework on that as well. 3 questions on page 706. Any issues with those? No, they're good? And then 3 more questions on page 707 that related to the same stuff, but were a little bit of a step up in terms of difficulty in the first set. Any issues with those on 707? Number 3? Okay. Any others? 2 and 3? All right, number 2 says, what's the energy of a 10 nanometer photon? First thing I want to do there, Liam, is circle the nanometers because I know I want to convert that to meters. Okay. If you look on your data sheet, in the middle of your data sheet, it's going to give you some metric prefixes, some SI prefixes, and one of them is an N. It says an N, a nano, is 10 to the minus 9. So what I want to do in this case is just simply replace the nano, the N, with times 10 to the minus 9, right? So this 10 to the minus 9 replaces the N. So it becomes 10 times 10 to the minus 9 meters. I want to find the energy of that. What variable were we just given? What variable is that? Janessa? That's right? Yeah, it's lambda. It's the wavelength. So we've got lambda. We're looking for energy. We're just going to say E is equal to hc over lambda. What value of Planck's constant do you want to use? Really, we could use whatever we wanted, right? because it doesn't specify what our answer should be in. But if we look at our answers here, we can see that they've done it getting an answer in joules. What value of Planck's constant do you want to use now? Yeah, let's use the 6.63 value only because it gives us an answer of joules. So we multiply those together. We divide by 10 times 10 to the minus 9. We should get that value of 2.0 times 10 to the minus, is that 17? Yeah. Is that okay?
Yeah, no, I just totally missed it.
Okay. And 3 says, how many photons of green light with a wavelength of 550 nanometers are required to deliver 10 joules of energy? How many? How many? Remember I told you something back about four-ish weeks into class. It would have been just into March. You were asked for the number of electrons. So remember I said, when you're solving for the number of electrons, when you're solving for the number of anything in physics 30, you're going to take a total something and divide it by the amount for 1. In the case of the number of electrons, it was the total charge divided by the charge for 1 electron. That would give you a number of electrons. Here we don't have a charge. Photons don't have charge. So we can't say total charge divided by the charge for 1. What are we going to take the total of this time? We're looking for a number, so it's still got to be total something divided by the amount for 1. What's it going to be? Total energy divided by the energy for 1. The total energy is 10 joules. Now we got to find the energy for 1, which is E is equal to hc over lambda. Okay, we're probably going to go joules since we're dividing 10 joules by something. 6.63 times 10 to the minus 34. Joule seconds times 3 times 10 to the 8. Divided by 550. Once again, Liam, it'd be 550 times 10 to the minus 9. And you don't have to remember that number, right? You can check your data sheet and find that it's 10 to the minus 9. Get a number for energy there in joules. Take that number up here. 10 joules divided by that gives me 2.8 times 10 to the 19. Is that okay? Remember, anytime you're looking for a number of something, whether it's electrons or photons or anything else, it's the total something divided by the amount for 1, by the something for 1. So okay, whatever you happen to have, whatever seems to be convenient to divide those two. Just like when we're looking for a ratio or comparing numbers, always think divide. A little demonstration with Jazzy and our pieces of paper and our calculator and our hole puncher involved the photoelectric effect, a phenomenon discovered in 1887 by Hertz. Same Hertz we've heard of before, right? Guy that did the spark gap apparatus, guy who has the unit for frequency named after him. 1887, but not correctly explained for almost 20 years. Took till 1905, Einstein's miracle year, to have this correctly explained. The photoelectric effect essentially says this: when light strikes a piece of metal, or other materials as well, but particularly metal, an electron or electrons can be ejected sometimes. Not all the time, sometimes. Hertz said if the electron wasn't being ejected, then, well, clearly we need more energy. Right? The electron's not being ejected, the electron didn't get enough energy. So let's give it more energy. Hertz said, give it more light. Give it brighter light. That's more energy, right? You get your flashlight that has the batteries kind of dying on it. You shine it on the piece of metal. Electrons aren't being ejected. Get new batteries for your flashlight. That's going to give your light more energy. That's going to cause electrons to be ejected. But it doesn't. It doesn't work. That's the prediction, but the observations that were made between 1887 and 1905 didn't confirm that. They contradicted that theory. So we knew that theory was wrong. We just couldn't figure out what was right. Enter Einstein in 1905, who said, the energy, he said, Hertz is right in a sense. He said, if the electrons aren't being ejected, we need more energy. But the second part of Hertz's argument is what's wrong. We don't get more energy from having more light. Einstein said, we get more energy from having more frequency. In other words, we don't need more of it. If we have a little bit of light that's striking a piece of metal and it's not causing electrons to be ejected, we don't need more of the same kind. We need something with a higher frequency. We need a different kind. If red light isn't causing it, let's try blue light. Something with a higher frequency, with a higher energy. That's where we get the energy from. If that frequency of EMR that we now try is above a certain minimum frequency necessary, and therefore a certain minimum energy necessary, that minimum frequency that we call, by the way, the threshold frequency, then an electron will be ejected. In fact, we find that for one photon above the threshold frequency, one electron is ejected. And for 50 photons above the threshold frequency, 50 electrons are ejected. And for 10 million photons above the threshold frequency, 10 million electrons are ejected. As contrasted to one photon below the threshold frequency where no electrons are ejected, or 50 photons below where no electrons are ejected, or 1 million photons below the threshold frequency where no electrons are ejected. So below the threshold, nothing happens no matter what, ever. Above the threshold, one photon, one electron, 50 photons, 50 electrons. The threshold frequency is the minimum EMR frequency necessary. We can say the minimum EMR frequency or the minimum photon frequency necessary to eject an electron. The symbol for the threshold frequency is F0. We might call that, Jack, in the UK, F0, right? You ever hear that? F0, F0? No? Okay. Frequency, we know, is pretty closely related to energy. So if we have a minimum frequency of photon necessary, then we also have a minimum energy of photon necessary. And that minimum energy we call the work function. So we're going to just do this. Put some ditto marks. Work function is the minimum EMR energy necessary to eject an electron. Now, listen carefully. If frequency is F and energy is HF, then minimum energy would be H times minimum frequency, F0. Right? The work function, the minimum energy necessary to eject an electron, the energy that's used up in the process of ejecting the electron, equal to H times the threshold frequency. We can also make that to HC over lambda. What would we call that lambda? HC over lambda, F the threshold frequency, minimum frequency, F the threshold wavelength. If it's not going to be a minimum, anything below a certain frequency causes electrons, anything above a certain frequency causes electrons to be ejected. Anything below a certain wavelength causes electrons to be ejected. Why is it maximum wavelength and minimum frequency? John? Good, because they're inversely related to each other. So as frequency goes up, wavelength goes down. Okay, anything above the frequency causes it, anything below the wavelength causes it. Now, what are you going to measure this in, joules or electron volts? Well, usually whatever you want. 6.63 value for Planck's constant gives you an answer in joules. 4.14 value for Planck's constant gives you a value in electron volts. Just restates what we've talked about, right, with our little demonstration and over the last page of notes here. When you're below the threshold frequency, nothing happens. When you're above the threshold frequency, something happens in a 1-to-1 ratio. 57,112 photons, 57,112 electrons if you're above the threshold frequency. 57,112 photons below the threshold frequency, 0 electrons are going to be ejected. Now, what if we amp up the, hold on 2 seconds here. Let's just finish this, okay? What if we amp up the photon frequency even more? We're not just above the threshold frequency, we're way above. It's not just the calculator in the demonstration, it's the hole punch in the demonstration. It's still a 1-to-1 ratio, still. But the electron that's ejected isn't going to be the same, isn't going to have the same characteristics as it was when we had the photon that was barely above the threshold frequency. This time, the electron is going to be more energetic. More electrons are ejected from more photons, still a 1-to-1 ratio, but those electrons will be more energetic if the photon is more energetic. Okay, we'll pick it up there on Monday, guys.